Senior developer on the Bitbucket team at Atlassian, focusing mostly on the server-side stack. He has a special interest for performance, elegant algorithms, and operating systems. To explain interrupt-driven development to us, please welcome Erik van Zijst.
Thank you. I'm Erik. I work at Atlassian, work on Bitbucket. And for those who don't know, Bitbucket is a free code hosting site for Git and Mercurial, private and public repos. And today I want to talk about the importance of responsive web apps. Not specifically web apps, but I'm going to talk about the from the background and context of my work, which is still web apps. But so the examples I'm going to use will be from Bitbucket. Like the techniques I'm going to talk about apply equally well to non-web apps. Now, I want to start off with this tweet, which showed up on my timeline recently, which seems to suggest that we are significantly slower than the competition, which took me by surprise. And this is a tweet, so obviously there's no context, there's no detail, there's nothing at all to substantiate what this appears to claim. But at the same time, I'm sure that Stephen wasn't making this up, and he was actually measuring something. So I quickly went over to our performance dashboard. You can see that at the top there, that's Bitbucket. And for that entire week, I looked at our average response times. Yeah, and as you can see, for that week, our average response time was about 123 milliseconds on the server. Then I hopped over to GitHub, looked at their publicly published numbers, and for that same week, they claimed 139 milliseconds. And so, that's nearest makes no difference equal. So there's nothing in here either to suggest that, we are so much slower. So I had a closer look, and I discovered that Stephen works for a company that writes a product that integrates with both these services. And on our end, they rely on a small number of APIs, one of which, admittedly, is indeed very slow. Now, luckily, that API endpoint doesn't get a lot of traffic, and or maybe that's not so lucky. But as a result, the poor performance doesn't really have much of an effect on our average response time. So what he was seeing was real, but it wasn't really representative for our service. But unfortunately, it is that small number of that small portion of really slow requests that in some ways have the biggest effect on the usability of your site. Your average may say that you're doing well, but it's the slow requests that get people in trouble. Like those are the ones that break pages, those are the ones that break integrations with external applications, and public evidently get people to rant about it on Twitter. So it goes to show that average numbers when it comes to response times are really misleading. It's not the fast request that people complain about, but for every couple of fast requests, you've got a really slow request. Those are the ones that break things. So it gives you a full sense of accomplishment, I guess, looking at those average numbers. It's a little bit like, looking at the rainbow and saying, well, the average color of the rainbow is whitish, which may be true, but it's a pretty pointless way of looking at a rainbow. And it's similar with slow requests. They have the biggest effect on your site, so you should be looking at those. Forget the average. Look at 98 percentiles, maybe even 99 percentiles. In fact, it's even worse. Like some requests literally run forever. Like if they're stuck in an infinite loop or in a deadlock, then they're never going to break out of that. Or maybe they're doing a stupendous number of redundant database queries, which, by the way, is a very common problem on database-driven applications. Every time you hit one of those, they take out one of your threads on your web server or your worker processes on your web server. And after a while, you'll have nothing left to service other requests. And you've basically, you got a DOS on your site. But to prevent this scenario of doom, many web servers, or some web servers, have a built-in failsafe, like a watchdog, that monitors long-running requests. And whenever they exceed a certain timeout, they kill those requests to prevent, a DOS. Now we run Gunnycorn, the Gunnycorn sync worker, which comes with a default 30-second timeout. After 30 seconds, if a request hasn't returned yet, it hard kills that worker process. And it does it by sending a kill signal, which is equivalent to typing kill-9. It's a signal that you can't catch or ignore in your application. You can't even detect it. And so it always works, which is very good, of course, if you use it for a failsafe. but it has the consequence that the program being killed has no ability to log any useful information. And so in our case, we don't even know these things happened because we don't log the time it takes to run these things. We don't know what they were stuck on, so we have very little to go on to fix these things. But they are the most important queries or requests on our site. So we needed a way to make these things visible at the very least. So we know that they occur, we know what they were doing, what they're stuck on, and then we can do something about them. So what we did was we experimented with an alarm signal handler. What we did was at the start of every request, we started an alarm signal for 28 seconds. And then on the way out, we canceled the signal again. Now, what that means is that if we're stuck in a very expensive request, then after 28 seconds, we basically tell the operating system kernel, because this goes beyond Python, to interrupt our program. And when that happens, the kernel will invoke our signal handler, which you see at the top of that code snippet. And so we regain control no matter what it was doing, whether it was stuck in a deadlock or you're doing database I/O, it doesn't really matter. After 28 seconds, that code gets invoked. Now what we do there is we just raise an exception, and we raise an exception that we know isn't caught anywhere. And the consequence of that is that the request blows up with an uncaught exception. So to the user, there's not much difference, right? He still gets a 500 error. The page still fails, just as he otherwise would have 2 seconds later when Gunnycorn would have killed it. But to us, there's a big difference because now it blows up in sort of a controlled way with a normal Python exception, and those things get logged, right? So we've got our web server hooked up to Sentry, and every uncaught exception immediately ends up on our Sentry dashboard. So now we had a real-time log of all these timeouts that occurred. So we got a feel for how big the problem even is. And what's more, because they're complete stack traces, we can even tell what they were stuck on. So when we turned this on, it's been running for quite a while, but when we turned this on, this is one of the things that turned up. So this is a fragment of the stack trace of a long-running request on our ChainSet API. Now our ChainSet API gives you a paginated view over all the commits in the repository. And the pagination works by offset. So the client provides an offset and a page size, and then the client controls the navigation. Now to help the client determine when they have reached the end of the set, every response returns the total number of commits in the repository. And that's where it goes wrong, because what you can see there at the top of that backtrace, what we do to compute the total number of commits in the repo, we basically call list on repo history. Now what that does in Bitbucket is it loads up every single commit in the repo inside of a big list in Python. And then eventually we do length of that thing. Now you can imagine that that's not going to scale very well, even though loading a commit doesn't include loading up any diffs or content from the repository. It loads just the metadata, but you still have to load that stuff from disk. So if you have twice the number of commits that you need to load, it takes twice as long. Until eventually, if only you have a repository big enough, you get in this trouble. So if we insist on returning the total number of commits, we must find a cheaper way of getting to that number. Ironically enough, so you can see here that this is Mercurial in this particular repo. And ironically enough, in Mercurial, it's very trivial to find the total number of commits in a repo, because in Mercurial, all the commits are sequentially numbered. So all you need to do is look at the highest number, you're done. So in other words, there's no excuse really for this thing to blow up the way it does. This is just bad coding on our part. Fortunately, the solution isn't as simple, because we also support Git, and in Git, there is no such shortcut to get to that number, and the only way to count the number of commits in a repo is to actually count them one by one. So we're back to square one, we still time out. Now, eventually I had to conclude that we were just committing to too much information. We couldn't commit this, we couldn't return this number reliably. In most cases it will work fine, sometimes it just doesn't. And so we had to take it out. Now there was more wrong with this API, and we have since rewritten this thing. This is deprecated, there is a new API, and the pagination in that works differently. It's no longer offset based. Every response contains an embedded link to the next page, and the last page obviously doesn't. So we sidestepped the whole problem, and it now runs in constant time. And that's an important observation. So basically, if you just look at that dashboard with the timeouts coming in, if for every problem that you see, you just rewrite the code to run in constant time, then you basically solve the problem. If you do that for every timeout that you see, eventually you end up with every code path running in constant time, which is pretty good, because Now you've got a predictable upper bound in execution time, and by definition that sort of that becomes your new 100 percentile. So you've solved all your problems, you'll never have any outliers again, you'll never have any performance problems again. Obviously it's not that simple, right? Oftentimes, or sometimes, when you end up and you sit down and you try to fix a bad piece of code, it turns out that it's really hard to refactor that properly. Like maybe you've worked on sort of legacy code bases and you've come across code that really hard resists being refactored properly. And as you sit down and you try to fix it, your changes ripples out through your code base. And as that happens, it takes more and more time, and it becomes more risky too, because with every change you might break something new. It's also possible that maybe the problem isn't so much in your own code, but it's in the dependency that you use, or external program that you spawn or something, or maybe it's written in something in a language that you don't really master that well. These are all sort of factors that can make it really hard to address these problems properly. Another set of things that can influence this are environmental issues. So in Bitbucket, to keep things fast, we use a lot of caching on various levels, and we use memcached for that. So we rely quite heavily on memcached. But we're not very smart, and when we use memcached, we don't actually version our cache keys. And what that means is that whenever we deploy a new version of our production code, which we do several times a week, we are forced to flush all of our caches. And you can imagine what happens on a very busy site when you just flush all your caches. It leads to a short but very heavy spike in load and also timeouts. And we can fix this by not being stupid and properly version our cache keys. But I'm mentioning it because it's sort of representative for a whole class of sort of environmental issues or influences that can influence load. For instance, like maybe you got expensive housekeeping jobs running occasionally on your servers. Maybe you do backups of some sort, or pre-compute indexes, or all kinds of things that can cause the load to go up. Maybe you got maintenance with people logging into servers and running all kinds of things. That too can have an influence on the load. And all these things are sort of hard to anticipate and predict and do something about in the code as a developer. And then there is maybe the biggest problem of all. There's input, unpredictable input that comes from users that you need to process. So in our case, for instance, that is people that think it's a good idea to push 50 gigs of binary Photoshop files into a Git repo. And then we get in trouble if we try to render a diff or even access any of those files. It's also us trying to linkify any content that is provided, like typed on the UI by users. So for instance, if you type an issue description or a commit description or like a comment on a pull request, all that stuff, when we render it, we scan it and we look for patterns that look like commit hashes, user names, other repository names, and when we find them, we turn them into hyperlinks to ease navigation. The way that we do that is we simply use regular expressions. So we run a whole bunch of regular expressions against any piece of user-typed input on the site. And regular expressions have a very unpredictable sort of runtime behavior. The time it takes to map, to run a pattern against something depends on the complexity of the pattern. It depends on the input and the combination of the two. So this example, for instance, seemingly innocuous, will run longer than this talk. So while it sounds very, very easy and very nice to just rewrite everything to run in constant time, there are many factors that sometimes make that impossible to do. But it's important that we focus on that small number of really slow requests, because again, they have the biggest impact. And so what we really want to do is we want to look for sort of a pragmatic way to regain some control over those cases. And what we've seen looking at many of these timeouts is that we saw that in many cases it would have been okay to interrupt a long-runner request, skip over the heavy bit, and continue with the rest, and then eventually serve a page that just lacks some of the data. It's often better than not doing anything at all and blowing up. So what we did was we sort of ran with the idea, and we took our alarm signal handler from earlier, and we turned it into a generic library that lets you time box any chunk of code. So what you see here is, we call it interrupting cow, and here you see it on a program that has a busy loop. We wrap the busy loop in a 2-second timeout, and after 2 seconds we raise runtime error if the busy loop doesn't exit. It doesn't exit, and so we blow up as expected. Now, timeouts are re-entrant, so you can nest timeouts. Here you see a 20-second outer timeout raises one type of exception, which wraps an inner timeout, which has a smaller timeout, which raises a different kind of exception. Inside of there, we do an operation that is potentially very expensive. Maybe it runs in time, maybe it doesn't. If it doesn't, we catch that exception eagerly, and we do something else instead, which hopefully is cheaper. You can also see that you can use float literals for timeouts. You can also use quota objects. And a quota, what it allows you to express like a time interval that you can then reuse and share among multiple invocations of timeout. And so every invocation of timeout can only use as much time as is left in the quota. This is very useful if you use it in loops, as we'll see later on. So let's see how this actually works. So remember our linkification problem? That's becomes even more difficult because we allow users to supply their own custom regular expressions on Bitbucket, so they can link anything to any external system that they run themselves. Maybe they've got their issues in fog bugs or something. They can link that. So what we've done, we don't want to ditch this functionality. So what we've done is we've written our linkification in such a way that we process every document progressively. So we replace one instance of the pattern that we find, then we replace the next one, et cetera, et cetera. And if at any given point we get interrupted, that's fine. We just use whatever we've got up until that point. So sometimes you'll have a commit description that is partially linked, but not completely. And here's how that works. So at the bottom here you see we've got a timeout of 100 milliseconds. And in there we call replace. We pass in a document, a regular expression, and an action. In this case, we turn it into a hyperlink. Now, inside replace, what you can see is we only replace a single instance. And we cut the document in half. So the first bit and the second bit. The first bit we apply the pattern, and the remaining document is basically recursively fed into ourselves until the entire thing has been processed. Now, on every level of the stack, we anticipate the exception, the timeout. And so you can see that we eagerly catch timeout exception, and when it occurs, it's fine. We just swallow it, but we cease any further recursion. We return, we end up with something that is always usable, and will have some or all of it linkified properly. Good thing is that we'll never spend more than 100 milliseconds on this problem, no matter what kind of regular expression people use. Now, Bitbucket is all written in Django, most of it, and so we spend a lot of time in Django's templating engine. And so we wanted to be able to use time boxing directly in templates. And so we've written a time limit tag that basically lets you do that. So a time limit tag takes two sub-fragments, and it will render the first one if there's enough time. If there isn't, it will render the other one. And here you can see how we use it inside of a list. So this fragment basically renders a list of commits, and for every commit, it renders a bunch of properties. One of the properties it renders is the diff stat. And the diff stat of a commit is the total number of lines that are affected by that commit. It's very expensive, potentially very expensive to compute, because you essentially have to build a whole diff and then count the lines in the diff. And it's very hard to predict the runtime of that because there's really no upper bound. Like a larger commit will take much longer to compute a diff stat for. So what we do here is we allocate a quota, a 1 second quota in this case. And we use that inside of the loop. So we just wrap the diff stat part in a time limit. And so no matter how long the commit list is, no matter how complicated the commits are, we are only ever going to spend 1 second processing diff stats. And for the remaining commits, if we run out of time, we'll just render diff stat not available. We think that's better than blowing up. Now, I'm not advocating you should start wrapping everything in timeouts, and that it's sort of a silver bullet, because it's not. In many cases, or in some cases, there's really no sort of viable lower quality of your data that you can use as a substitute. However, if you do, you get some really unique aspects. So this kind of programming works well with legacy code, or code you can't really change effectively. May not even be your own code. It gives you sort of a generic approach to dealing with these issues, right? So whether the core of the problem is a busy loop like CPU-bound stuff or I/O-bound stuff or whatever it is, it gives you a generic way of dealing with that, because the time boxes work just the same. And it sort of maps nicely to Python's optimistic approach to programming. Like in one of Python's philosophies sort of is, it's easier to ask for forgiveness than permission. So just go ahead and try to do what you think you want to do and assume that it's going to work. And if it doesn't, well then deal with it by catching the appropriate exceptions. It's sort of in contrast to the more pessimistic look before you leap philosophy that characterizes some other languages. Now, likewise, time boxing sort of allows you to continue to use really powerful functionality that works fine most of the time, but not always. In the remaining cases, you've got your time boxes to keep things under control. And another interesting characteristic is that these things play very well under server load. So typically, if you have a server with very high load, everything sort of slows down. And when that happens, you tend to get a buildup of pending requests and jobs. As that happens, that usually compounds the problem even further. So time boxing basically makes sure that you cap your execution time, so therefore the throughput on your side remains the same, and so you avoid the whole problem. So sort of to summarize, page render times are very unpredictable. There's usually lots of external factors that contribute to it. Some of them will be very fast, some of them will be very slow, and even though the number of slow requests is just a tiny fraction on your side, they have the biggest impact. So you have to, look at those specifically. And do everything you're used to doing. So refactor bad code whenever you can. Pre-compute expensive stuff, and even remove functionality or push back on functionality that you just can't do in a scalable way. For instance, that ridiculous list that we did on that change list page. But then on top of all that, whenever that isn't feasible and you really want to offer this powerful functionality, you can consider time boxing. That's all I have. Thanks a lot for listening. Are there any questions?
Thanks, Erik. That was
There's
great.
any time for questions, I guess. But
Yeah, we have a couple of minutes left for questions. We'll start. Do you want to? You can go first.
Hi, yeah. So you spoke a lot about obviously timeouts in code. And I'm just wondering if there's any scope, I suppose, for adding other types of interrupt, as you see in other areas of computer science, perhaps interrupting it from another thread or another process, whether there's scope for that within interrupt and cal.
Yes, I think there is, and it's because there are quite a bit of. I didn't have time to cover all the caveats because using signals has quite a few catches. And for one thing, it doesn't play nice with threads. So if you have a threaded web server, then this thing doesn't really work very well. So in other words, the question is there scope to use interrupts between threads? Yes, I guess there is. Interrupt doesn't do it right now, but yes, I guess if you have sort of a background thread that keeps track of runtime execution and then interrupts the proper threads, or I don't know, basically the same as what you do with signals, but on the thread level. Yeah, that could be very interesting. Another thing which would be very interesting, which I thought about but never realized, is to sort of have resource constraints around memory, right? So you say, run this piece of code, but never use more than 100 megs of memory, for instance. Look, we have a lot of these problems with ridiculously large repos. Haven't gotten to that point, but yeah, there's definitely scope for that.
Let's see. I'm not too sure if my question's relevant anymore, but can you sort of detect the server load, then selectively run different algorithms based upon the quality of the data you want to return?
Sorry, what was that? One more time?
Well, you could detect what the response rate is from the servers, and then if everything's really going super, super quick, you can use the more complete program response, or if you're under load, you can use the cheapo one.
You mean sort of turn it around? If you got more time, do a more expensive thing. I guess, yeah. I could never really consider that in our context because we always run out of time. But yeah, I mean, yeah, of course, it would apply equally well, I guess, if you could program that.
A couple of more questions over this side. We'll go over here first. Sorry, guys.
Just a quick question. What's the overhead like for interrupting cal?
I'm going to say it's properly negligible. These things they're system calls, but they're very quick. And sometimes they're even used as a sort of a profiler. So you do it a lot of times. You build up a statistical breakdown of where your execution takes place. And so it's very, very quick. And in this particular case, it depends on how many time boxes you use in your code, I guess. But I don't think you'll ever see it show up in a profiler.
We still had a couple more questions over here, and we do have a couple of minutes, so.
In the case of a timeout, the client, I guess with the client's having to deal with, two types of responses. And I just wondered how you document that, or how you communicate to the client that, hey, there's a bit more complexity for you potentially involved. And I guess there's a bit of tension there as well, because you're putting some work on the client in order to deal with these two types of response. I just wanted your comments on that.
Yeah, for sure. We sort of make it easy on ourselves, but obviously, yes, we know basically we give an incomplete result, and how is the client going to deal with that? And it's hard to give sort of a generic answer to that, because it really depends on the thing that you're rendering. But to give an example, we use this. What we started out using this for most on Bitbucket was our diff page. Like whenever you look at a commit on Bitbucket, you get a single page that has all the files and all the diffs on a single page. And so again, there's not really any upper bound, so these pages can get infinitely long pretty much. And so we scope all that stuff. And then in that particular case, what we do is we render a page. You'll have some of the file diffs, which usually is enough for sane diffs, but for some insane diffs it isn't. And then the remaining files are basically they're sort of buttons that you can click and then load that one thing. Right, so in that particular case, it's fine, because you serve it as a page, not as an API endpoint, and there are buttons to basically complete the missing data. In API endpoints, it's sort of sometimes we document it. Like the diff thing also applies to the API, and you can get a specific error status code basically if you couldn't compute it in time, and then you're basically in that particular case we basically we're sorry, but we can't do this.
Sorry guys, we don't really have much more time for questions, so if you do have anything you'd like to ask, feel free to come up and speak to Erik. We have a coffee mug and some coffee beans from Ritual Coffee here for Erik, and thank you very much for that. That was
All right. Thanks
really
a lot.
good.